When you interact with artificial intelligence today, you imagine weightless code, floating silently in an ethereal digital cloud. You picture clean silicon, sterile laboratories, and pure, abstract mathematics. But strip away the polished user interfaces of today. Look deep beneath the pristine architecture of our modern digital world. What you will find at the very bottom is not weightless software at all. It is dark, heavy, and fiercely mechanical. In 1957, at the height of the Cold War, a Cornell University psychologist named Frank Rosenblatt did not write a software program. He built a 5-ton mechanical monster. It was called the Mark I Perceptron, a towering industrial monolith of 400 glowing photocells, heavy electric motors, and a labyrinth of copper wire, designed to physically mimic the neural pathways of a human eye and brain. When this spinning metal beast successfully taught itself to recognize simple shapes without human programming, the New York Times ran a historic headline declaring that humanity had built an artificial brain, one that would soon see, read, write, and become conscious of its own existence. Before AI lived in the cloud, it breathed as a ticking, 5-ton engine of pure metal. The quest to engineer an artificial mind was never just a cold, scientific experiment. It was a bitter, deeply personal philosophical war, waged between two boyhood rivals who had walked the exact same hallways at the Bronx High School of Science in New York. On one side stood Frank Rosenblatt, a maverick psychologist who looked at the biological brain and saw an inspiring, magnificent chaos. Rosenblatt believed that true intelligence could never be dictated from the top down by human programmers. He argued that you could not sit in a room and write a rigid code for intuition, or mathematically program the feeling of recognizing a face. To Rosenblatt, the only way to build a thinking machine was to build a physical, sensory organ. A machine that could look at the world, make embarrassing mistakes, and learn through brute trial and error, dynamically adjusting its own internal copper dials like living biological synapses. On the other side of this intellectual divide stood Marvin Minsky, a brilliant MIT mathematician who looked at Rosenblatt's 5-ton, ticking metal hardware and saw a clumsy, primitive toy. Minsky was a purist. He believed that human intelligence was born from clean, symbolic logic and mathematical precision. He insisted that the true path to machine consciousness was not soldering wires or spinning potentiometers, but writing elegant, top-down software rules on sterile, digital computers. As Rosenblatt's self-learning machine captured the imagination of the global press, landing on the front page of newspapers around the world, the academic disagreement between these two old classmates curdled into open warfare. One man wanted to nurture a biological, electronic organism. The other wanted to program a flawless, logical calculator. The stakes could not have been higher. Both men knew that whoever won this debate would dictate the technological trajectory of the human species. And in the academic battle for the future of civilization, only one philosophy would be permitted to survive. For a decade, Rosenblatt's mechanical perceptron seemed unstoppable. But in 1969, Marvin Minsky launched a devastating counterattack. Not with a new machine, but with an unassailable mathematical weapon. Alongside his colleague Seymour Papert, Minsky published a landmark book titled Perceptrons. Inside its pages lay a rigorous mathematical proof demonstrating that Rosenblatt's 5-ton brain possessed a fatal, fundamental blind spot. To understand how Minsky destroyed the perceptron, you have to look at how the machine actually perceived the world. Geometrically, when Rosenblatt's machine made a decision, it did so by drawing a single straight line across a coordinate grid. Imagine a mechanical brain trying to separate red marbles from blue marbles, scattered across a table, using only a rigid, wooden ruler. If all the red marbles are on the left, and all the blue marbles are on the right, the ruler easily divides them. But what happens if the real world is complicated? What happens if you arrange those marbles in a checkerboard pattern? Red in the top left and bottom right, blue in the top right and bottom left. Try to separate the red from the blue using only that single, straight ruler. It is physically, mathematically impossible. You cannot draw a single straight line without trapping opposing colors on the same side. This simple, devastating barrier is known in computer science as the exclusive OR, or XOR problem. Minsky's proof was catastrophic. He mathematically proved that Rosenblatt's single-layer perceptron could never solve complex, non-linear logic. The revelation sent an immediate freeze through the scientific world. Governments, corporations, and military agencies panicked, concluding that self-learning machines were an expensive evolutionary dead end. Global research funding evaporated overnight, plunging artificial intelligence into a crushing, 30-year dark age known as the AI winter. And in 1971, just 2 years after his life's work was publicly disgraced, Frank Rosenblatt drowned in a boating accident on the Chesapeake Bay on his 43rd birthday. He died in the cold silence of academic exile, believing the world had permanently discarded his 5-ton brain. For nearly 40 years, the AI winter gripped the globe. The dream of a self-learning machine was dead, and Rosenblatt's name was quietly scrubbed from university textbooks. Yet, in the underground margins of computer science, a rebellious handful of researchers refused to abandon the biological model. Working in shadowy labs with minimal funding, they kept interrogating Minsky's famous 1969 equation. And as the decades passed, a stunning realization began to dawn on them. Marvin Minsky had been wrong about the future. The fatal checkerboard problem was not an evolutionary dead end at all. The limitation Minsky exposed was only true if you used a single artificial neuron, a single ruler. To solve the impossible puzzle, you did not need to abandon Rosenblatt's perceptron. You simply needed to do something beautifully, radically intuitive. You had to stack them. Imagine taking hundreds of those rigid wooden rulers and connecting them end to end. If you take multiple layers of perceptrons, feeding the electrical output of one straight line directly into the input of another, the machine is no longer blind. Suddenly, those straight lines can bend, fold, intersect, and curve around any complex data pattern in the universe. It was the geometric equivalent of shining hundreds of light beams from different angles into a dark room at the exact same time. The underlying mathematics of deep neural networks, the very architecture of modern machine learning, had been hiding in plain sight since 1957. Why didn't Rosenblatt do it himself? Because in the 1950s, a computer capable of calculating thousands of layered connections would have been the size of a city. The only thing missing was the brute, physical supercomputing power required to spin millions of simulated copper dials simultaneously. Humanity just had to wait half a century for silicon chips to catch up with Frank Rosenblatt's imagination. Today, we stand surrounded by the most explosive technological revolution in human history. We converse with synthetic intelligences that compose symphonies, diagnose complex diseases, map the human genome, and generate breathtaking cinema in seconds. It feels effortless. It feels like magic. But strip away the gleaming, sleek exterior of today. Step inside the freezing, multi-trillion-dollar server farms powering our modern world. Walk down the endless corridors of black glass and humming steel. What is actually running inside those glowing towers of silicon? It is not alien magic, and it is not Marvin Minsky's clean, top-down software logic. When you trace the code of today's most advanced AI models all the way to the bedrock, you find an overwhelmingly familiar architecture. Every time you speak to an artificial intelligence today, you are interacting with billions of Frank Rosenblatt's simple 1957 artificial neurons, stacked in deep, intricate layers, learning relentlessly through trial and error. The man who died in academic disgrace was right all along. The next time an AI answers your question, listen closely to the silence behind the words. You are not listening to a ghost in the machine. You are listening to the echoes of a 5-ton mechanical brain from Cornell, still spinning its copper dials, defining the future of the human world.